Okay, so here's an example of a two-dimensional force problem that is going to leverage a little bit about what we know about tension. And the mathematics in this one aren't it's not terribly difficult, but I am going to solve it entirely in symbols so that we can see the general form of this equation, and maybe you'll see why when we finally get there. All right, but we do have some numbers to work with. We're saying that with this lovely sign here, that the sign itself has a mass of 15 kilograms, and the chains are symmetric in that they make the same 70-degree angle with the horizontal on either side of the sign. So there's the chain right there, and we're saying if we took a little dotted line here and we measured this angle right there, then that would be 70 degrees, and doing the same thing on the other side, you'd have that equal to 70 degrees as well. All right. Now, the first step in any force problem, and we know that this is going to be a problem to do with forces because we're literally asking for a force in the statement of the problem, okay? But the first thing we do in any force problem is draw ourselves a force diagram. You don't necessarily need to do the thing that I'm going to do and take the sign over here all by itself, so it's literally a free body, and then grab yourself a different color, do blue, and draw in all of the forces. But you do need to have some diagram of the forces, or it's entirely too easy to lose track of what forces are acting and how they're related to one another. So we've got two different chains, and we know that the tension force is exerted along that chain, and that it's going to pull on the sign here, right? You can't push a chain, for instance. So, well, you can, but it's awkward. So here we go. I didn't quite draw that correctly. I got a better diagram in the next slide, but there's your two tension forces. I'll just call them FT1 and FT2 just to differentiate them. And there's nothing else touching this sign, right? It's hanging there. So don't start putting in normal forces and forces of friction and things like that. There's only two things contacting it. Tension 1, tension 2, two chains. And the only other force that can be acting then is our one force of distance, which is the force of gravity. Cool. Okay. Those are all of our forces. We could, again, repeat these angles over here if we wanted to be a little more explicit about that, but we've already written it down. And there's a prettied up version of that diagram. And these thetas that I've indicated here are going to be those 70-degree angles. But I'll leave it as theta because that's just a little bit easier to put into our algebraic expressions. Okay, we need a little bit more space to solve this out, so I'm going to transition to the next slide, and I'll carry this free body diagram with us. There it is. Lovely. And I've added some coordinate axes over here so that we know what our vertical and horizontal axes look like, okay, whether those are y or x. And remember, we want to find the tension in each chain. Here's our relevant bits of information, as well as this free body diagram, and we're ready to start writing down our sums of forces. Now, with a sign, what's the acceleration going to be? I'll give you 2 beats to think about it. Well, it's going to be 0 unless you've got another force acting, right? If it's not a windy day and this sign isn't being blown around by the air around it, well, then gravity and the tensions better all just cancel out so that this sign stays on the strut that is supporting it, okay? So if we want to know about the tension, we might think about which sum of forces to write down, right? And when I say which, well, of course, we want to split everything up into x and y components so that things are easier to deal with, right? Reduce it to a couple of 1D vector problems. And there's no real rhyme or reason to start with one versus the other. So let's just start with the sum of the forces in the y direction. And we know that that has to be equal to 0 because the acceleration is 0 for this sign. And there are three forces that have y components. There's going to be the first tension force, there's going to be the second tension force, and there's going to be the force of gravity. Now, I could have left these all as like little vectors and just summed them all up and not put in the information that we know about direction, but I just skipped that step. So we've got these two that are positive, so upwards in the y direction, and this one that is downwards, right, negative in the y direction. And we can write down, let's see, what do we know about this? Well, we know that F sub g is equal to m times g. And we know something about the components of these forces, right? That's going to be sine of theta. And this one will be F2T2 sine of theta. And that'll be minus mg. Now, if we look at that, well, we want to know what each one of these tension forces is. Now, if you look at that situation and you make a little bit of an intuitive leap, you might suspect what the relationship of those two things is going to turn out to be. But we may as well prove that it must be the case, right? We're kind of thinking, or we should be thinking, that those two forces are equal because they're both sort of both ropes, both chains are tilted at the same angle relative to the vertical or the horizontal. And the chains are the same, the angle's the same, so they both should have the same y component, right? And that turns out to be true, but we can actually get that given to us by the mathematics, but it's a little hard to see here. So the other tool, though, that we have in our pocket is that the horizontal forces also have to sum to 0. And that means that Ft2 x, right, the x component, so this little bit right there, okay, is in the positive y direction. The Ft1x is in the negative x direction, so that little piece of that vector right there. And then these two components have to be equal, right? Those are the only two horizontal components. And so there they are. And we know that those are cosine theta, and these are the same thetas. So the cosines just cancel out. And we learn that the magnitude of T1 and the magnitude of T2 must be the same. That's enforced by Newton's second law. Okay. Well, that means that if we take that fact and we apply it to this line, that we can rewrite this much more simply. We can just say 2 times ft1 sine theta minus mg has to equal 0, right? So we just had two factors of the same number, and I've written that out symbolically here. Okay, just a couple more steps here. If we add mg to both sides, sorry for the handwriting, and then rearrange things so that we have the force of tension of the first chain all by itself on one side of the equation. Well, we have to divide both sides by 2 sine theta to get that to be the case. And there we are. So this is technically the force of tension in this chain, but it's going to be the same magnitude, just different direction for this one. And so we're basically done at this point. All we really need to do is plug in our numbers and get our final result, which is something like 78 newtons. I'll have the exact number or a closer number on the next slide. However, let's check out a couple of things here that we want to be careful to take note of. All right? And actually, let's just advance the slide because it has all this information on there. So it's the same kind of stuff. There's the sum of the x components. Here's the sum of the y components. And you should recognize this algebra. There's that expression that we got. And there's the answer with one more digit of precision than I had on the last slide. Okay. Now, the number is, okay, well, is like a little over 4 newtons per pound of force. So it's not unreasonable that we'd have like, maybe 16, 17 pounds of force in each one of these chains when you have a 15 kilogram sign attached to them. The thing I want to take a look at, though, is the algebraic expression and what that tells us. Okay, so first, it tells us that the tensions are directly proportional to the mass of a sign. Okay, that should make sense, right? If we took down this sign, we put up a 30 kilogram sign, we would expect the tension in those chains to be bigger. In fact, we might need to go get heftier chains, okay? That makes sense, no problem. But then let's take a look at this. Remember that this theta is the angle between the horizontal and where the tension is. So as that goes to 90 degrees, well, let's see, sine of 90 degrees equals 1. So that would mean that the tension in the line would go to mg divided by 2, like if it was vertical, straight up and down, right? Theta equal to 90. That makes sense, right? So if you have two chains, they're straight up and down, so there's no x component. Well, they should each bear half the load, right, of canceling out F sub g. Cool. All right, so that end checks out. What happens if we take theta and we go towards 0 degrees? In other words, we mount the chains such that they're coming off like at this angle, or even a shallower angle, like really close to horizontal. What happens then? Well, sine of 0 degrees is just 0. And so you would have a tension that would be mg over basically nothing if you actually took and tried to make the chains horizontal. And so the required tension in the chains at that point, if you wanted an actually horizontal chain to do the job, would have to be infinite to make the sign not fall to the ground. Well, one, you're not going to find a chain quite that strong. And two, this should also make sense from just looking at the free body diagram up here. If you want to cancel out a downward vertical force, right, F sub g here, you need some y component to these tensions. And if you were actually to somehow achieve a horizontal attachment angle, so 0 degrees equals theta, well, then you'd have no vertical component. And so you could get infinitesimally close to 0 maybe if you had an infinity of force of tension in those chains. But it just doesn't make physical sense, okay? And the equation that we got for the tension backs that up, right? Backs up our intuition that that should be implausible. If you want a demonstration of this, take like a piece of string and wrap it around something, I don't know, it doesn't have to be that heavy, but something that's like a half a kilogram or something like that. And wrap the ends of the string around your fingers and just pull on it. And pull really hard. Pull as hard as you can. And if the thing in the middle isn't very weighty, you might be able to look at it and be like, I think I actually managed to pull on it hard enough and create enough tension to make it horizontal. But if that thing in the middle has any sort of mass at all, okay, you're going to be able to pull as hard as you want, and you're either going to snap that thread or you're going to cut the skin on your fingers where it's wrapped around your fingers, or some other uncomfortableness, and you'll see this physical result come right out of that little experiment. Okay, so that's one more example of a 2D forces problem. I hope it helps you attack the assignment for this week, and I will see you next time.